Okay, guys, finally, how do we write an efficient algorithm for edit distances in Python, right? And we already saw that we somehow need to create this sort of DP 2D matrix that's of size m by n, that at every index m comma n sort of represents the value of our edit distance call to that m comma n, right? So that says that we need to somehow create this 2D matrix sort of thing. So let's go ahead and create that. In the beginning, we want to initialize all of the values within this matrix to be false, right? Because all of these indices have not been visited yet. So we'll call false for I in range n plus 1, uh, and n because each of these is our columns. And now we want to create m rows, right? So for j in range m plus 1. So that gives us m columns. Um, and now what you see, the beauty of this is now that we have this DP framework, right? We can just copy over our code from edit distance naive, and we can sort of use it as a sub function, a sub method, or a nested function within our edit distance. And we'll change this name from edit distance naive to edit distance helper, just so we know we're talking about different functions. Right? And don't worry, those aren't the only changes we'll make, but here. So right now, what exists inside this is what exists inside edit distance is edit distance helper, right? Which is the same as edit distance naive right now. But the whole advantage that we were trying to create is to sort of get edit distance helper to pull from these DP, to pull values from this DP array, right? From this 2D DP matrix. And the way we do that is now we're going to say if DP mn is not equal to false. And the reason I'm saying is not equal to false is because these values can also be something like 0, 1, 2, something like that, right? So you want to be very explicit that if this area has not been initial, if this area has been initialized to some value, just return that value, right? Just return dp mn, right? And what if it's not? If it's not, then you go ahead and you do all of this. But before returning it, before returning your answer, store it in dp m comma n, right? Store it in the dp matrix, right? Don't lose that result. And then you can just return the dp m comma n. Right, and that's it. That's all it took for us to sort of convert that naive algorithm into our efficient algorithm. This is DP. This is an DP solution to edit distance. And yeah, let's go ahead and run this on our test suite. Oh, hold on, I might be doing something wrong. Oh, I forgot to call our main function edit distance on edit distance helper, right? So what we want our initial call to be is just edit distance helper on word 1, word 2, and we just want to start it off with m and n, right? Okay, so let's go ahead and now try and run this. Okay, so we see that we have the correct answers. We have 3, 5, and 3 for our 3 test cases, which we expected 3, 5, and 3, 4. Our runtime is not that much. And now here's the really interesting part, right? So as always, just maybe pause the video for a second, estimate how long it'll take us to run on test large. Bear in mind that edit distance naive on large took us 10 seconds to run. So yeah, 3, 2, 1. That's it. All it took us was 1 millisecond to run this. And that really shows better than anything else the advantage of DP algorithms over a naive approach. And all you had to do is you had to create this DP matrix sort of thing that sort of stored your DP's answers, right? So that you didn't have to go on recalling the edit distance helper and like make it go from the top of the tree to the roots of the tree to calculate its values. So one simple change and 2 simple changes within the naive algorithm gave you an algorithm which is so much faster. I'll leave you to analyze the formal runtime of the DP. It should be fairly straightforward. And even if you want to analyze the formal runtime of the naive algorithm, you can do so and compare the two. But yeah, I hope this was helpful. And I'll see you guys next time.